Yes, thank you for it. Good evening, everyone. I mean, it's not evening, let's call it an early night. So, I welcome you all to my webinar on language translator using neural machine translation. So, before I start, let's have three things wandering on mind. That is, how, what, and why do we need language translator, and in particularly, why do we use neural machine translation? So, to start with, let's one second. Sorry. Sorry for the disruptions. So, to begin with, let's get familiarized with few terms. Corpus. What is corpus? It is a large collection of relevant data. I assume it to be a large set of easy processing data. Probability. This could also be termed in mathematical terms. You can also call it like you can also define it like prediction or a possibility of an event considering all the other events in the sample space. Frequency. It is the occurrence of separate elements in the corpus. That is, it is the recurrence of an element. For example, let's take a sample set of random numbers from 1 to 10, and there are 1 5s, 2 2s, and 3 3s. And the frequency of the one in that sample space would be 5. That could be frequency. Vector. This is a mathematical term. So we could define vector as in relation of one point to another point in the space. So let's take a situation of a word to word. Let's consider word as a point, and uh, a relation between two words would also be called as vector. Let's assume vector in the form of matrices also. So to continue with word embedding. Word embedding is the process of relating one word to another in the process of computer readable form in the form of matrices. That is, processing of each word in numeric formats in the form of matrices to assign its value. So these are a few basic terms. Let's dive into few other basic terms. Perceptron, it is just the core of any neural network in the algorithms, supervised learning algorithms. So a perceptron is actually an artificial neuron of an algorithm or a network. I assume it to be uh, sorry sorry for the disruptions. Perceptron is basically consists of three major parts. One would be the starting point would be the inputs. While the inputs are fed within context vector, weighted vectors, and it is sent to an activating functions which would make it uh, bound in bound into a certain interval of let's consider minus to 5. All the values are put in the in the range of minus 5 to 5, and later decisions are made to which network should it connect, and that forms the core of neural network, and will the for basic calculations, we'll call it as neuron. Sequential learning. Sequential learning is a study of machine algorithms wherein it requires sequential inputs of data for the machine to learn sequentially. Then reprocessing. It is almost considered as when we input a large corpus of data, it has to be converted into binary readable form, and that is done in the pre-processing step. Tokenization. It is the process of just dividing the input text into token by identifying word boundaries. We know that every word has its own importance, and especially for learning a word meaning or a project like this would require essential values of the word in a certain format. So tokenization does that in the format of splitting into tokens, and it would count the frequency of it and find pattern of the words while assume ranks also, and also it forms co-occurrence of words in the matrices. I mean, it just tells you the importance of a word in a pool of words. So blue, It is an automatic evaluation of machine translation. Consider we have translated from English to French, and we have the target sentence and predicted sentence. So to match the so it is a indirect calculation of the predicted sentence as well as the targeted sentence as well. Now that we have got familiar with few basic terms of machine learning or deep learning, let's get into neural networks or neural machine translation. I said, why do we need neural machine translation, or in special, why do we need uh, a language translator? So there was a famous scientist called Warren Weaver. He once said that when I look an article in Russian, I say this is written in English, but it is encoded in some strange symbols. I'll now proceed to decode. This idea of ability to make anyone speak to anyone without the boundaries of language was the most applauding idea. And the basic and the most important goal of this automatic translation was to provide an error-free translation in order to preserve the meaning of the original source language. So that was a triggering idea for people to start language translators. And I said, you, why do we need neural machine translation? When they came up with this idea of translating languages, people started making algorithms in their own way and started triggering, making mathematical calculations as well as algorithms and many as such. One of that would be a word-to-word model. A word-to-word model was built in order to predict the exact meaning of the word into into a translated language. I possibly assume that it would be difficult for anyone to assume to understand the translated language. So it was lacking a few semantic and syntactic structures of the translated language. So they came up with statistical methods, and even they came up with a model called IBM 1 and IBM 2, which eventually failed. I don't call it fail, but was a improvement from a far better from word to word translation. Then there came an model called phrase-based model. This model would not only convert word but also could translate phrases. A phrase could word by word have a different meaning, but eventually at the whole would have a whole new meaning. So that was an advantage of phrase-based models. But later on, when phrase-based models used large amount of memory, it was also a drawback for it. So then they came up with neural networks. Why neural networks? Because it would form a whole new
Shashank.
networks of. Sorry, sir.
Shashank. Hi,
Okay.
Shashank. Yeah, I think
Yes, sir.
your
Yes, sir.
screen is not shared. So,
Uh,
under sharing, can you please click on show screen? I think that stopped.
sir, is my screen visible, sir?
Yeah, it is showing the previous image. What happened? Yeah, now some change. Yeah, now I see some change. Yes.
Okay, okay, okay. So, sorry for
Are
the
you changing
disruption,
the
sir.
screen or you're not changing the screen? I am seeing the title slide, Neural Machine Translation.
Yes, sir. I'm about to start it, sir.
Oh, I see. Okay, I thought you were discussing some slides which are not. Okay, that's fine. I'm seeing the title slide,
Okay.
Neural Machine Translation. Okay.
No, I thought of sharing. Okay, okay. Sorry for that, sir. So people started using neural networks, and this neural machines advantage was it could take only fraction of memories or compared to phrase-based models. So they started with neural machine translation. So we have got, why do we use neural machine translation? Let's get a deeper dive into neural machine translation. It is the mechanism of modeling the machine translation process using artificial neural network. As I mentioned, artificial neural network was based for many algorithms or in deep learning processes. So neural machine translation used encoding decoding models in order to catch the semantic and the syntactic structures, while also preserve the meaning of the words and the meanings inside the neural network. So let's take a situation. Let's assume we want to convert from English to French. So Let's assume for a sequential learning of data at every time intervals like T1, T2, the both models would separately train itself so that it could understand the all the words and the meanings of the words as good as possible. So it started in an encoder-decoder model. Mm. So what is encoder and decoder model? Encoder is actually making a single neural network of all the of all the words or into certain value and embedding them in the form of neural networks and forming a single network neuron. And decoder also does the same part, while the both gets mixed or understand itself mutually by conditional probability and making the values of the words define each other in different in the perspective languages. Mm. So as I mentioned, all sentences were encoded into fixed size vectors into a single neuron, a large neuron, and it used fraction of memory compared to SMT models, and that was which I mentioned. And performance of this decreases as the sentence of the source sentence increases. Yeah, this was the point. For a neural network to continue, it is actually a large neural network, and when you start predicting, the accuracy starts decreasing due to the lack of its performance or in order to predict it as it lacks memory status. So what does encoder actually use in machine learning term or deep learning terms? It uses a network called RNN network. We all know that neural network forms itself, but it does not use previous states for it. Uh, so RNN key features of RNN are it uses its previous states as its present input in order to predict the next word. So this was an advantageous process for sequential learning because uh, in our for a syntactic or a semantic structures we need the previous sentences to in order to predict the next words or in order to get a meaningful sentences. So encoder maps the variable length sentences into fixed sentence vector, and this was what I mentioned to network. And after it gets into a network, a bigger RNN network, it is mutually trained using the conditional probability of the targeted sentence given the source sentence. That is P of the foreign language which we need to get translated using the source sentence English. So this is the mathematical function of an RNN. So when we feed in input to the function x of t, it is where corresponding to its weights, it is uh, fed into an activation cell which uses its previous set of activation cell as an input along with its hidden weight layers, and that with the submission of both the input and the previous state, it would give the output using context vectors. So let's take it this way. Consider an input sequence of x1 to xt and an output sequence of y to yt. So we have this hidden activation cell, which is usually a sigmoid or tan function or complex LSTM or GSM. We will talk about LSTM and GRU cells later. So basically, RNN trains to predict the next word in the sequence. So it goes on with the sequential learning as well as it would take its previous states in order to predict the next words or the next results. So that was it, and the mathematical term would be p of x is equal to summation of from t1 to the whole t of prediction of the next word using considering the whole set of data, previous data. So we know that a neural network is formed on the chain, and when we unroll it, we have a set of data in the form of a neural network. And eventually, when we do the calculations, there is an error caused which is E of t. So Uh, to minimize the error, we start updating the values of u, v, and w, which is the weighted vectors or the context vectors or the hidden layer parameter units. So we start updating the values with the mathematical terms using the back propagation through time theory, through time concept, wherein this is a small sample for changing the value of v. It is similar for w and u as well. So let's consider the equation as we said, h of t is equal to w of into product of x of t plus u into product of h of t minus 1, the previous state. So it used a sigmoid function or the tan h function as s of t, while z of t would be v of s of t. It is an optimizer kind which uses s of t. So uh, error is calculated by the softmax layer y minus y log of y of t. So to derive the values for v, we use a concept called maximum or minimum theory. So in this, we start doing a chain rule process. Chain rule process of often we take a d of e of t and we start deriving it to y of t and continuing with the z of t derivative and then corresponding parameters or the updated weights. In Then we obtain an output in order to derive v, that is t of out into the s of t, which is the weighted vector of the final output. So this turns out to be similar for even W and U as well. So the basic problem of this was when you start updating the values of it, eventually the values would decrease, and so that it start diminishing, and the neural network starts forgetting its own values. So this to prevent this, they started creating LSTM models, which is long short-term memory. It is the
So just to
variant of
augment,
an
yeah, just to
sorry.
augment that previous slide. So I hope audience
Yes, sir.
understood what is BPTT. So for audience purposes, BPTT is back propagation through time, because RNN, unlike a traditional neural network, is a recurrence over time, right? So next time
Yes, sir.
step is dependent on the output of previous time step. So the gradient, the back propagation of gradient also happens through the concept of time steps. Hence, we call it back propagation through time or BPTT algorithm. The concept is very similar in a regular neural network where it backprops across layers going backwards. Here it backprops over time in effect, and hence it's called back propagation over time. And you see the partial derivative is similar to the partial derivative of a regular neural network going backwards. And you attribute part of the gradient to the previous and the previous and the previous layer, and then you do the weight adjustment in those subsequent previous layers. Just augmenting that, kindly continue.
Okay, thank you for it, sir. To continue, the gradient values or the weighted values would diminish eventually, and the neural network would start forgetting, and thus it would become independent, which is not needed, which is quite irrelevant for us to continue with sequential learning. So they started creating a model called LSTM, which is uh, sorry. Sorry for it. Let me continue.
Yeah, there is some background noise coming, Shashank. I don't know if it is reducible or not, but just letting you
Okay.
know, there is some background noise,
Okay,
maybe
sir.
family in the background.
Okay, I'll try, sir.
Okay.
Is it clear now, sir?
No, no, your voice is clear. There is some background people talking maybe in the family. So just letting you know. I
I'll
mean,
try.
maybe it's not, it cannot be fixed, but that's all right. I'm just letting you know.
Okay, sir. Uh, Okay, to continue with, sorry for the disruptions. Uh, they started building LSTM models, which is long short-term memory models. In this, the key feature was it had a chance of either forgetting the previous memory or to sustain the previous memory in order to continue the sequential chain. There are actually three main parts. The first part would be the forget gate partition, while the second would be the input gate partition, and the third would be output gate partition. Here, the inputs are fed with C of t, which would be memory. And for example, if x of t value would be 0, we would say it as a forget gate. And if it is close to 1, we would assume it to be carried forward. So that was the first layer of LSTM model. While the inputs are also fed again to a and get through sigmoid function and tan function, which would vary its value and show its importance in the next slide, in the next neural networks. So so after it does complex calculations, those are sent again to tan h and the sigmoid functions in order for the output to continue, so that it does not vary the range between let's say -5 to 5 values or -1 to 1 values. And then the c of t is carried to the next function, and h of t also is carried. So in this format, we have an option of continuing with the previous memory and also with the next hidden layer units. So in this function, this is a schematic diagram of and then associating hidden new layer activation cell. And for that, we would say if the values are closer to 1, we would say it to preserve, like to update the values of the weights in the neural networks. And if it is closer to 0, we would say reset the gate and continue the network. This would avoid the complex issues of forgetting the memories, and thus the network would understand the short-term dependencies to have reset gates that are frequently active, while for the long terms it would update the values and would continue for it for a longer time. So from this we could obtain the meaningful sentences, as in uh, we uh, we lost our context in RNN. So this is basically a schematic diagram of how encoder and decoder works. Encoder, let's continue with encoder once. Encoder actually takes in the fed input and converts them into computer readable form, or gets embedded word padding is done, and later on later on uh, sorry, am I audible?
Yes, very much audible.
uh, Okay. So RNN the inputs are fed in the form of matrices, and the computer starts learning in the sequential format from one another, and it is all the networks form in itself into a complex neural network, and has a context vector with it, have a context vector at the end, which could be the last one, sees the summary of hidden states at time t and has encoded all symbols in the sequence. So it actually predicts of the same language. It actually predicts the next word of the same language using its previous context. And to continue with, the decoder does the same thing, but it uses context vector as its hidden state and starts continuing to sequentially learn the structures of the translating language. So it actually has the probability of predicting the next word of the translating language using considering the context vector of encoder and also the previous state of its own language. So that was the decoder part. How do we like merge in both the encoder and decoder part? We use a parameter which is JFI, or that this is a mathematical equation which would merge both the encoder and decoder part. Actually, it is a conditional probability which is used in order to set the values for each word and get to know its meaning in both the languages and show its importance in the form of numeric values. So j of phi would be max of 1 by n log of probability case of y of n using the sentence which need to be translated, and it uses BPTT for reducing the errors, and that is done through BPT processes, and so we obtain the sequential sentence and this target sentences pairs. So it also uses a mechanism called attention mechanism. Let us consider this passage, and we have few major key aspects as in objective, attention, and this words important or the mechanism. These all are weighted across the neural network and are fed as an important part so that the decoder does not uh, deny its importance in translating the languages. So this was one major key aspect of RNN using LSTM models. So to continue with, let's take a code demo of our project. This is our project, and this is a language translator project, and we are using Keras models in order to do the complex operations and the machine deep learning training. So these are the relevant libraries which we used for learning the which we used for in further for learning the data. So in the first context, we would eventually take a large stack of data or a large corpus of data and try to read it in the first instance. Then we split the data into lines in order to make it more readable and for more easy processing of data. So this would convert it into the form of arrays into the numerical value, and then we are taking samples of around 50,000 data, 50,000 samples in order for a clean and more understandable translation. So in this process, we do text processing, which is eventually debugging the hyphens or the exclamatory marks, which tends not to be much necessary or much relevant to converting data. And this is the text cleaning. There is text cleaning happening around it, and in the final formats, they are converted into a readable form of either in the uppercase or in the lowercase for usual common instance, for usual common usage. Sorry. Later, these texts are converted into a sequential formats in order for it to learn in a sequential manner. So to embed it in a format, we would take the length of it, and for embedding purpose, we would take its sentence length across the uh, lists of sentences in both in both languages. So as I mentioned, tokenizer would uh, define the value or would define the word values in in the form of numericals. So this actually does tokenizations processes eventually, and will output the vocabulary size of our targeted language and the prediction language. So now comes the model building process. In this, we use scikit-learn in order to split the data, and now let's start to embed them in the form of numeric values, and so that process would be called as encoding sequence format. So we encode this in the format of numbers. Then we would start building our main network, that is neural machine translators. So we start defining it in a we start training it defining it in a sequential manner, while the second process would be embedding them in the form of numerical values. Then we use the RNN variation LSTM models in order to learn them in to learn them in both vice versa. And this repeat vector would eventually join merge both and
But yeah,
create.
Shashank, can you increase the
Sorry, sir.
font of the screen? You can increase the font of the screen. Control plus.
Okay, sir.
Font
I
size
would
is too
do it,
small.
sir. Okay.
One more. Yeah,
Is
this
it
is
okay,
good.
sir?
I think this is fine now. Yeah, yeah.
Okay, sir. Okay, so this was the basic architecture of NMT model, and whatever I have explained, this was the basic libraries which would be used in order to train the model. So we are using RMS prop for learning it in a much decent manner. So it uses an optimizer called RMS prop in other way to mention. And uh, sparse category entropy, it is actually used for an hot for to convert into hot encoded format, which which actually used a lot of space previously, and for now it would use fractional memory, and this was the advantage which we're speaking about. So to continue with, this was saved in the the format of H1 format, and the training starts to happen. After we have done our training, it turns out to be that the losses are decent, are almost equal to one another, and this shows that it was almost a decent translation. So now we'll start to start to make predictions on our test samples. As in, we have split the data into 80% for in training and for 20% to test the data. So we start to load the data, and eventually it would be in the form of matrices and in the form of array and number formats. So this format should be converted into human readable form, and that is done using this array formats, this algorithm. So eventually we start to predict the sentences as we tried. So we take the starting head of it, and we see that there is an almost accuracy, a decent accuracy of predictions of words, as in he asked me to do it. There is a language that is in German, and we have translated into English. The actual one would be this, and the predicted model would give us this values. We are almost closer to accurate, and if we use a good if we use a good regularization technique and a clip of all the overfittings, we would get a fitted models or a decent structural manner model. So this was the predicted values as of now. Let me pause it for a minute and just show you how the predicted values would go. These were the predicted values, and we can tell that this is pretty much a good, decent algorithm, deep learning algorithm in order to predict languages, and that was a neural machine translation. Apart from this, neural machine translation could also be used for this were the schematic structures of it. And so apart from the machine level translation or language translator, it could be also used for summarizations or code generation, or also to test the papers, or I mean to say a quiz type of papers, or uh, the ones which we write for exams. It could also be used as an application for both testing the papers, I mean the matching of data, and replicating its scores as in the output. And that was it. Thank you for it. Sorry, sir, I'm done. That's it.
Okay, audience, any questions for Shashank? There was quite many concepts discussed, so it wasn't a small session. There were many concepts discussed. So Shashank did mention that this kind of encoder-decoder architecture has multiple applications, such as text summarization as well, apart from language translation. So any other questions for this session? So Shashank is a third-year BTech student at BMS College of Engineering. And so you can see at third year also we are developing good experts in AI, and they will be doing increasingly more sophisticated projects over time. Okay, so I don't see any other questions coming up. I hope you enjoyed that session. Thanks, Shashank. Well done, and good hard work and great presentation. Thank you for your hard work, and thank you audience for joining. We look forward to seeing you in our future webinars. Have a good day or good night as the
Yes,
case may be.